So, hello everyone. My name is Karthik Kharbanda. I did my MTech from ISC Bangalore and I'm one of the faculties at iitiansgateclasses. So, in this video, we are going to look at the solutions for compiler design, the questions which came in GATE 2020. Okay. So in this video, what we'll do is we'll try to look up the questions, and in the questions I'll try to explain whatever the concepts were used and what are the possible shortcuts that you can apply to solve these problems. All right. So we'll start with solving the first problem. So what we'll do is you can pause the video, okay, try the problem yourself, and then you can unpause the video for every question and you can see the solution. Okay, so this is the first question which came in GATE 2020 for 1 mark. Please try this question yourself, pause the video and try this question yourself. All right, so I hope you paused the video, you tried the question yourself, and you got some idea as to what the question is saying. Okay, so let's understand the solution for this. So now they are saying, consider the following statements. These three statements are given, and ultimately the question is, which of these above statements are true? Okay. So what we'll do is, we'll tackle one statement at a time, and we'll try to see if that statement is true or false. All right. Okay. So the first statement is, symbol table is accessed only during lexical analysis and syntax analysis. All right. So see, symbol table is what? Symbol table is a data structure in which all the variables that you have in your program, okay, all the variables, all the function definitions, all of them are actually stored, okay, and every phase of the compiler, okay. So let me just explain you the first three phases. So the first phase of the compiler is called lexical analysis or lexical analyzer. The second phase of the compiler is called syntax analyzer. And the third phase is called semantic analyzer. Okay. So I'll not be going over to the rest of the phases. Okay. So these three phases are enough to understand the first statement. So they are saying only lexical analysis and syntax analysis will access the symbol table. Okay. So in lexical analysis, what you do is you try to store whatever symbols you come across, you try to store those symbols as it is in the symbol table. So this phase will actually put in some entries in the symbol table. Okay, let's say this is the symbol table. All right. Now syntax analysis. In syntax analysis, the grammar comes in, right? If you remember, the grammar will come in syntax analysis. So basically, you're trying to give structure to the program. If you're trying to check whether the structure of the program is correct or not, okay? So this will also give in some entries to the symbol table, okay, depending on that structure. Suppose we have a statement int a, okay. Int a means a is a variable of type integer, okay. This is defining the structure, and hence this thing will be input in the syntax analysis phase. All right. In the syntax analysis phase. So statement 1 is saying symbol table is accessed during lexical analysis, syntax analysis. Yes, this is true that lexical analysis will access symbol table, syntax analysis will also access symbol table. But when you come to semantic analysis actually retrieves some of the information from the symbol table. Okay, like checking whether you have multiple declaration or something like that will be checked during syntax analysis. So syntax analysis actually tries and retrieve those values which are stored by lexical and semantic analysis. So we are sure that semantic analysis will actually retrieve some values from the symbol table. Hence, analyzer also accesses symbol table. Okay, but in the statement they are saying only lexical and syntax. So statement 1 is false because for the simple reason semantic analyzer will also access symbol table because it want to retrieve some information about the variables. Okay, so statement 1 becomes false. Now consider statement 2. Statement 2 is saying compiler Compilers for programming languages that support recursion necessarily need heap storage for memory allocation during runtime. Okay, during runtime. Now, if you remember, for memory allocation during runtime, we have two kinds of storage available. Okay, one is stack and one is heap. Okay, so this statement is saying it has to support heap storage necessarily. Okay, well, this is not true. The reason being, if we have support for stack, then also we would be able to allocate memory during runtime, even if only we have stack. Okay, so heap storage is not necessarily required. Okay, stack plus heap storage, both of them will actually allocate memory during runtime. Okay, so for this particular reason, statement 2 is also false. I'll just summarize it. Stack and heap both will be required. Okay, if both are not there, then you cannot allocate memory during runtime, or you cannot allocate memory dynamically. Okay, so necessarily heap storage is not required. Okay, not necessarily. Okay, it is required but not necessarily. So because of this simple thing, statement 2 is wrong. Okay, let's see the statement 3. Statement 3 says errors violating the condition, this condition, any variable must be declared before its use, is actually in syntax analysis phase. Okay, so to understand this statement, what we have to do is we have to check what actually happens during syntax analysis. And you keep this point in mind that I want to check the error what any variable must be declared before its use. Okay. Okay, so let me just rub this part. Right. So what happens during syntax analysis? During syntax analysis, what you do is you try to check the structure of the language, okay, using the grammar that you have. Okay, so let's say if I have some statement like this, int a, and I say, again, if I say, okay, so again I say, let's say the error was any variable must be declared before its use. Okay, so let's say you're saying a is equal to 1. Okay, these two statements are done. Now during syntax analysis, when you do syntax analysis, will only check the structure of the statement, int a semicolon. So it will pass. Okay, this structure is correct. Okay, and it will independently check this statement. Okay, it will independently check the statement. It will see, yeah, this is an assignment operator, this is a variable. So on the LHS of an assignment operator, I should have a variable, and on the RHS, I will have some variable or value or an expression. Okay, so it checks this, it will pass. Yes, this is also correct, right? And now suppose I give the program only this thing. Okay, only this thing. So it will just come to this line, check this. Okay, a is assigned some value 1, a is assigned some value 1. So that is all right. Okay, that is all right. Syntax analysis will pass this statement. Okay, because what it will do is it will go to the symbol table. And remember, in lexical analysis we already stored what was a, because this statement will go through lexical analysis as well. Tokens will be created. So a will be passed in lexical, in when you come through lexical analysis, a will be stored as a symbol, and you will just assign value 1 here. Okay, so syntax analysis will pass this thing. Now this error, of course, will not be checked in syntax analysis, so the statement becomes false. Third is false. Now the real question is, when will this error be declared? Okay, if I give you only this statement, okay, if I don't give you, okay, so if I just give you this without mentioning anything about this, okay, this is not mentioned in the program. If I just give you this statement, okay, so syntax analysis is going to pass. Okay, now how will we be able to check this error? So this error will be checked during semantic analysis. Okay, what semantic analysis will do is it will now, in the semantic analysis phase, it will check, because I told you in the first statement, I told you in semantic analysis we try to retrieve some value from the symbol table. Okay, so it will check a is assigned 1. Okay, so it will bring on the meaning of the grammar and all, everything it will bring. and it will check A is assigned 1. Now from the symbol table it will check whether A is an integer or not, because 1 is definitely an integer, right? So during semantic analysis phase, it will try to check whether A is an integer or not. And then when it tries to check symbol table for that value, it will find that since this statement was not there, A is not assigned any data type. A is not assigned any data type. And for this simple reason, it will throw an error saying that A is not declared before its use. A is being used over here, but it is not declared. This is why this error will be caught in semantic analysis. This error will be caught in semantic analysis. So I hope this small point is clear to everyone, right? So this is why statement 3 is false. I'll again summarize statement 3. The error will not be checked in syntax analysis. Syntax analysis just check the structure of the statement, whether A equal to 1 is structurally right or not. This should be a variable on the left hand side of the assignment, and this should be some expression or some value. So it will say, okay, this is good. I will pass this down, no error over here. Okay. But when semantic analysis phase come, it will throw an error. Okay. So I hope all the three statements are clear. All the three statements in this are false, and hence option D will be right. Okay. So this came for 1 mark in GATE 2020. All right. So I hope this question was clear to everyone. Let's move to the next problem. All right. So this is the next problem. Now pause the video, try this question yourself. All right. So I hope you all tried this question, and now let's see the solution for this. So they are saying, consider the language this and the following statements. Okay. So what I'll do is I'll try to write the language and get some idea about what the language is saying. So language is what? Language is a power n, where n is greater than or equal to 0, union a power n, b power n, where n is greater than again equal to 0. So if I expand this language and write the strings which will be there inside the language, so it will be C. If n is equal to 0, this is epsilon. If n equal to 1, a. If n equal to 2, then a square. Or you can say a. I'll not write a square. So if n is equal to 3, this is again a, and so on. Okay. Union, the second language, the second part will be what? If n is equal to 0, then this will be epsilon. Epsilon means empty string. Okay. Nothing is there. Empty string. Okay. And then you have n equal to 1, so it will be a power 1, b power 1, that's ab. Then you have n equal to 2, a, b, b. Then you have n equal to 3, a, b, 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 and so on. So now you got some idea of what this language, what kind of strings this language is representing. All right. So these are the strings that this language is representing. Now, if I want to mention a small point, if you know what is regular expression, what is regular language, what is a finite automata, and what is push down automata, so you will be able to check that this is a regular language. Okay. This is a regular language, and this is actually a context free language. Okay. Only this part. Okay. This is a context free language, and that too a deterministic one. Okay. You can easily create a push down automata. Okay, you can easily create a push down automata to solve this. So what you can do is, in that push down automata, every time you see an a, push it into the stack, and every time you see a b, pop it out of the stack. Except for epsilon, we have to handle epsilon separately. That's a corner case, and we can do that. All right. So this is a deterministic CFL. Now if you remember the property, so, okay, so let me just mention this also, that a regular language, okay, or a language which is accepted by a finite automata will also be accepted by a push down automata. The reason being, power of a push down automata is more as compared to power of a regular language. Okay, so these concepts are from theory of computation. This question was a mix of theory of computation as well as compiler. Okay. So everyone knows that power of PDA is more than power of finite automata. So you know that if I try to give this language to a PDA, it will be able to accept it. Correct? So what I want to say is, let's say this is language 1, okay, L1. This is what language 2. So what I want to say is L1 union L2 is there. L1 is also accepted by a PDA, hence it is deterministic. And L2 is also accepted by a PDA, hence this is also deterministic. All right, these two are deterministic. So if I take L1 union L2, then union operation is closed under DPDA. That means deterministic PDA. It is closed under DPDA. So you can say L1 union L2 will also be a deterministic CFL using that property. Okay, deterministic PDA. Now, either you can use this property, or what you can do is you can try and build a deterministic PDA, which will be easy for this combined language. Okay, and you will see that you are able to successfully build a deterministic PDA. Hence, this language L1 union L2 will be a deterministic context-free language. Okay. So where is the, yeah, this is the statement 1. So hence statement 1 is correct. Okay, it is a deterministic context-free language. So if you read the statement 2, it is saying context-free but not deterministic. That means they are saying in statement 2 what they want to say is that this language is non-deterministic context-free. Well, that's actually it. If a language is deterministic, of course a non-deterministic PDA can also accept that, but they are saying not deterministic. This is why this statement has to be false. Okay, they are saying not deterministic PDA. Well, that part of the statement is not true, hence second statement is false. Okay, now we'll see this is not LLK. Okay, so let me just give you a brief idea about what LLK is. Okay, so if you remember, LL is a top-down parser. Okay, this L and this L. What do we mean by these L's? So first is this is scan from left to right. This is the meaning of first L. Okay, and the second L is you use the leftmost derivation from top to bottom. Okay, that means these are what? These are top to bottom parsers. Okay, so use leftmost derivation from top to bottom, going from top to bottom. Okay, that means you start from root and you go to the leaves. Okay, so this is what LL, and the K over here represents the number of look aheads that we have. Number of look aheads. Okay, number of look aheads will let you make the decision as to what you have to do next. Okay, so this is what we mean by a general LLK parser. Okay, so I hope this point was clear. Now we'll check the language. I'll again draw these strings in the language that I mentioned earlier, A, and so on. Okay, next is union of AB, AABB, AAA, BBB, and so on. All right. Now, if you see in this language, if I compare the respective strings, the first string from the above one and the first string from second one, and this and this and this and this. Okay. Let me compare these three. Okay. So let me say I'll put some value for K. Let me say if my parser is LL1, that means I can only see one ahead, one look ahead, and I have to decide which path should I take. Okay, which path should I take? So if you see in this language, let's say it is LL1. So that means if you have a string A, if okay, so let's say if you are at string AA, that means you are currently at this A and you're trying to look one look ahead. Okay, fine. And you are at this string and you're trying to look one look ahead. If we compare these two strings, now the problem is if I just use LL1 and see the next string, I will not know whether my next string is AA or AABB. Okay, I will not know just by sitting at this point and checking the next string. I will not know whether this is A or AABB. Okay, and this is creating some confusion for the LL parser. Okay, because of course when you try to write the when you try to draw the parse tree for these two, the parse trees will be different. So LL1 will not know whether this string will be there in my language, the language that I need to accept, or whether this string will be there in the language. So this is why LL1 will be confused. Okay, if we take an LL2 for this guy, so it will see, okay, it will see next two symbols to make the decision. So that means this is A, and it will take the next string which is null, which is epsilon, nothing is there, right? And it will check, okay, A is there, B is there, so it will be able to differentiate between these two. Okay, so LL2 parser will actually be able to differentiate between these two, but again LL2 parser will fail here. It will not be able to identify whether after two A's do I have an epsilon, that means I don't have anything else, or do I have B's lined up. Okay, this is why LL2 parser will fail here. Similarly, LL3 parser will pass this thing, but LL3 parser will what? Fail here. Okay, and for this simple reason, if you keep on going like this, you will understand that LLK parser will not be able to differentiate, it will not be able to differentiate a k length string. Okay, k length string from these two. Like if I have k length AAAs and if I have k length AAAs and BBBs. All right, so it will not be able to differentiate between these two, and hence LLK parser will not be able to recognize this language, or will not be able to basically parse this language. Okay, it will not be able to differentiate. Hence, if I go back to the statement 3 again, it is saying that is not L is not LLK, which is true for any K. Because if you see these two languages, both of them are infinite languages. Okay, so basically you need your K to be infinity to identify them, which is not a feasible value. K should be something which is of finite value. Okay, so this is also true. It will not be able to recognize the language. Okay, so if you see, option C will be correct, second is false, first is true, and third is true. So I hope this solution is clear to everyone. Yeah, so let's see the next problem now. All right, so this is your next problem. Now pause the video, try this question yourself. All right, so I hope you tried the question yourself and you got some answer. So I'll tell you the answer. The answer will be 7 in this case. Now, see, there are two ways to solve this problem. Okay, so they are saying this is the grammar given to you and number of reduction steps taken by a bottom-up parser, and you have to parse basically this string. This string is given and you have to parse this string. Okay, now, the first step, which is the longer one, and remember this question was for 1 mark. Okay, so first step is a longer one. So you take the strongest bottom up parser, that is your canonical LR parser, CLR1, or you simply call it LR1 also. Okay, CLR1 is also called as LR1. You take the strongest powerful bottom up parser and you try to write everything. So first you try to write your LR1 items, you try to draw the DFA for this language, and then you try to create that table. After that you check this input and you try to solve and see how the bottom up parser will be able to build the parse tree in the bottom up fashion. Okay, so now you know that this language, okay, so let me just mention this point also. First thing is you use LR1 parser and solve it. Now the problem with this method is very lengthy when especially the question is for 1 mark, so it is not really feasible to do it this way. Now if you remember, whether it's a top down parser or a bottom up parser, always the languages which are recognized or which are or the grammar which is accepted by these parsers, the grammar has to be unambiguous, right? Now when we are saying that this language can be recognized by a bottom up parser, that means I am saying that this language will be unambiguous. Okay, and when I say that the language is unambiguous, then there will exist only single parse tree for this language. Okay, so the better way is since they are not mentioned any, I don't have to tell anything about the bottom up parser. What I'll do is I'll simply use the grammar and draw the parse tree for this string. Okay, because I know there will exist one parse tree. That means if this language is top down, if it can be solved by a top down parser and by a bottom up parser, both the parsers will give you the same parse tree. Okay, so ultimately if I draw the parse tree, I'll be able to tell you the number of reductions. So let me draw the parse tree. Let me just copy this on the next slide. SASB, and it is D, I suppose. Yeah, D and then B, and this is B. All right. So these are the two statements. These are the two statements or productions which are given for the grammar. Okay, and the string is AAADBBB. AAADBBB. Now I'll try and draw a parse tree. Now we don't have any method to draw this. This you have to uh, you know draw manually, and it will come through practice. So I'll start with my starting symbol, which is S. I take this ASB. Again, see, I need three A's. So I'll draw, keep on drawing till the third one, ASB. Okay, this is B. Let me just redraw it. I'll require some more space. One moment. All right. So S is ASB. Again, S is ASB. Again, S is ASB. Okay. Now I have to use some other productions. Now see, I have three A's. So for this S, I'll use the other production, which is S derives D. Okay. So this is B, this is B, and this is B. Okay. Now what do I mean by a reduction? Reduction means you started from A, D, B, 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 and you have to reduce and create the parse tree in the reverse order. So first reduction will be I'll reduce my D to S. Okay. Second reduction will be I'll reduce my these to this. Okay. Third reduction will be I will reduce this guy. Okay. And then similarly you will follow. Now I'll tell you a shortcut also. Whenever you have a parse tree, number of non-terminants, or you can say number of the non-leaf nodes, that means the internal nodes, will be equal to number of reductions. That is the shortcut you can apply. Number of non-leaf nodes will be equal to number of reductions. So what you can do is you just simply count the number of non-leaf nodes. So this is 1, this is 1, 2, 3, 4, 5, 6, and 7. Okay, so these are 7, and hence number of reductions will be how much? 7. Okay, so this technique is a much faster way compared to if you start drawing your LR1 parser, LR1 items, then DFA, then create the table and so on. It will take little more time. Okay, so I've told you two ways. I hope these both the methods are clear to you. All right. Okay, so the answer in this case would be 7, as 7 is the number of non-leaf nodes which are there. All right. So let's move to the last question which came for 2020. Yeah, okay, this is the question, and this came for 2 marks. All the other 3 questions were for 1 mark. This came for 2 marks. Okay, now try this problem yourself. Pause the video, try this. Okay, so I hope everybody tried this problem. So this problem is based on synthesized attributes and inherited attributes. Okay, so let's see the problem. There are two productions given to you. A belongs to PQ and A belongs to A derives PQ and A derives XY, and 5 non-terminals are there. Fine. 2 attributes are there. S is a synthesized attribute and I is an inherited attribute. Okay. Now every non-terminal may have multiple inherited attributes, multiple synthesized attributes. Okay. So more information on this you can find when you do semantic analysis phase. All right. Now consider the following 2 rules. Rule 1 is this is the assignment given to you. Okay. These things you will see when you come across semantic analysis. Okay, because semantic analysis is syntax analysis, the structure plus the meaning. Okay, this is the meaning. Okay, these things define the meaning to those grammar statements, grammar productions. Okay, Now, which of the following is true? Which of the following is true? Now, I'll tell you one important property about synthesized and inherited attributes. Okay, synthesized attributes. These attributes take value only from their children. Okay, so if I have some production, let's say I'll take the production in the question only. A belongs to PQ. That means I can write A dot S. A dot S is equal to P dot S. This is correct. Okay, because synthesized attribute can take values from their children, from the attributes of their children. Okay, A dot S is equal to P dot S plus Q dot S. This is also correct. Okay, because again, parent is taking value from what? Parent is taking value from their children. Simple as that. Okay. Now let's see the difference. Let's see the inherited attribute and we'll see the difference. So in inherited attributes, what you have is, let's say I again take this production. Okay. So A dot I, okay. Now we'll not say A dot I. The reason being, in inherited attributes, a non-terminal or an attribute can take value either from its parent or from its siblings. Okay. So that means if I write for P dot I, P dot I can take value from whom? Either it can take from A dot I. This is correct. Okay. Then P dot I can take value from Q dot I. This is also correct. Either it can take value from its children, or Q dot I can take value from P dot I, or P dot I can take value from Q dot I. Okay. So either the siblings can take value from each other. Either the siblings can take value from each other. Okay. So I hope these two concepts are clear. Now I'll go to L attributed and S attributed. Okay. What is SDT? SDT is syntax directed translation. SDT. Okay. So there are two kind of SDTs. One is S attributed and the second one is L attributed. Okay. So the definition is pretty simple. So in SDT, S attributed SDT only uses synthesized attributes. Okay. It only uses synthesized attribute. So if some statement is mentioned and you want to say that statement is S attributed SDT, then it should only use synthesized attributes, and you know what is the property of synthesized attributes. Okay. All right. You know that what is the property of synthesized attribute. Okay. Now for L attribute, for L attribute, for L attribute, you can use either synthesized attribute. Okay. The statement can have either synthesized attribute or you can have inherited attribute, but little modification is there. Okay. You have to modify the inherited attribute a bit. So the modification is what? In inherited attribute, the right sibling, or if I say this belongs to P dot Q, this guy can only take values from the left sibling. Okay. When you take values from the sibling, a sibling can only take values from the left sibling. Okay. So if I write something like P dot I is equal to Q dot I, this will not be inside L attributed. This will not be allowed in L attributed SDT. The reason being, P is a non-terminal. Okay. And the attribute of P is taking value from what? The right sibling. That is not allowed. Okay. But Q dot I is equal to P dot I. This is allowed. Okay, because here the right sibling is taking value from the left sibling. Okay, this is allowed. Okay, so this is one small modification how we used inherited attribute in L attributed SDT. Okay, so all these concepts are required to solve the question which I have discussed. Okay, the last question for 2020. Okay, so we'll see. Now see, check the rule number 1. It is saying inherited attribute I is equal to A dot I plus 2 is fine. A dot I. So P can take value from its parent. Yeah. because A is the parent, P is the child. P can take value from this parent, so this statement is fine. It is because they are saying in the option check for L attributed. Okay, so this is perfectly fine with inherited attribute, so this is all right. Okay. Now you say q dot I is equal to p dot I plus a dot I. So p dot I is what? P is here, a dot I is here. So q is taking value from either its left sibling or from the parent, left sibling or from parent. So this is also fine, right? Right sibling is not allowed in L attributed. So this statement satisfies the L attributed SDT conditions. Okay. Now you check for this guy. A dot S is equal to P dot S plus Q dot S. Yeah, this is also fine because this is actually a synthesized attribute property, and in L attributed I told you that synthesized and inherited, modified inherited, both are allowed. Okay, both are allowed. So that means rule 1 is perfectly all right, no problem in rule 1. So let's see now rule 2. So rule 2 says x dot I is equal to a dot I plus y dot s. Okay, so you see x dot I is here and you're saying a dot I plus y dot s. You're basically trying to give value of, you're taking the attribute of x and providing the value of the parent as well as the right sibling. Well, you remember that right sibling value is not allowed. Okay, right sibling value is not allowed. So this statement is not correct. Okay, this statement is not correct. Now you see y dot I is equal to x dot s plus a dot I. So y dot I is equal to what? X dot s. This is fine, and a dot I. This is also fine. Okay, because y is on the right hand side. See, y is on the right hand side, and you are assigning value of the left sibling as well as you are assigning the parent. So this is fine. This statement is all right, but this statement is wrong because here we are assigning x dot y dot s value to x dot I, which is the right sibling. This is not allowed. Okay, so this is why rule 2 is false. Okay, this is why rule 2 is false. Hence, if you see, option B will be correct. Rule 1 is L attributed, but rule 2 is not L attributed. Okay, so option B is correct, and this is the answer for the question. Option B is correct. Okay. All right, so this is all we have for this video. So I hope everybody liked this video. So if you have any doubts or if you want me to cover any more concepts on compiler, okay, in detail, please mention it in the comment box and we'll get back to you as early as possible. If you like the video, if you really enjoyed it, then like the video, comment on it. Okay, a positive comment will be good, and subscribe to our channel. Also, please share the content so that all of the people who are preparing for GATE, they can benefit from this. Okay, so I'll see you in the next video. Yeah, thank you everyone.